this is John Whitaker for the probability class, and this is our 15th video lecture. And we have just begun looking at some limit laws, and we had some facts that we had listed before, in particular two inequalities, Markov's inequality and Chebyshev's inequality. And I want to review those and do an example to start off with this lecture. So here, let's remember that Markov's inequality what did it say? It said that if x is a non-negative random variable, and a is some number greater than 0, then the probability that x is greater than or equal to a will be less than or equal to the expected value of x over a. And then we had Chebyshev's inequality. And it said if x is a random variable with finite mean, that means expected value, and variance, finite variance, sigma squared, then the probability that the absolute value of x minus mu is greater than k will be less than or equal to sigma squared over k squared, and that's for any or for all, for any k greater than 0. That's a true statement. Okay, so that's what we have. And so I want to do an example that involves these two inequalities. Now this is something straight out of our text. It says, suppose we know that the number of items produced in a factory during a week is a random variable with mean let's call this random variable x, okay? With mean expected value of x equal to 500. Okay, so the first part, it says, what can be said about the probability that this week's production will be at least 1,000 items. Okay. So we'll go ahead and handle this part first. And so here, what's being asked of us is the probability that x will be greater than or equal to 1,000. What we can say is that's going to be less than or equal to, by Markov's inequality, the expected value of x over 1,000, which equals to 500 over 1,000, which equals to 1/2. So the probability that that this week's production will exceed 1,000 is going to be less than or equal to 1/2. Okay? And this is by Markov's inequality. Okay, we got part B to look at. And here's what it says. It says, if the variance of the week's production is known to be 100, then what can be said about the probability that this week's production will be between 400 and 600. Okay, so here's our, that's part B. Okay. Here's the solution. Okay, so for the answer, what's being asked of us is what's the probability that the week's production is between 400 and 600? And that's what's being asked of us. And what I want to do is I'm going to use Chebyshev's inequality. And what I need to have is the mean involved here. The mean was 500. So this is the same thing as if I subtract 500 from each one of these parts of this inequality, that the probability that minus 100 is less than x, which is less than 100. Whoops, I forgot to subtract 500 from the middle. Okay, that's symmetric kind of set. We have minus 100 on the left and 100 on the right. That's the same thing as the probability that the absolute value of x minus 500, the mean, will be less than 100. And that's equal to 1 minus the probability that x minus the mean, 500, will be greater than or equal to 100. And that's something that Markov, the second part, not Markov, but Chebyshev's inequality will tell us about. So here's what we'll look at next. We'll note that the probability that the absolute value of x minus 500 is greater than or equal to 100, that's going to be equal to, well, it's this variance, and it said the problem of the variance is 100, okay, over this is going to be less than or equal to, over this number squared, and that's by Chebyshev's inequality. Okay, so by Chebyshev's inequality. And this is equal to, this is 100 over 1, 0, 0, 0, 0, or 1 over 100, which equals to 100. So, the probability that the absolute value of x minus 500 is going to be less than 100, which equals to 1 minus the probability that x minus 500 inside absolute values is going to be greater than or equal to 100. Okay, so here, this quantity right here is less than or equal to 1/100. So what we're going to be taking away, whatever we are going to be taking away, is going to be less than 1 over 100. So this is going to be greater than 1 minus 1 over 100, which equals to 99 over 100. So that's what can be said in this example. So the probability that this week's value of production, I should say, of items, is between 400 and 600 is going to be greater than or equal to 99%. So that added information. Well, there is some information that I probably should have provided to you earlier. And actually in homework problems, for homework 2, some of the items that we're dealing with are defined based on what I'm going to tell you here, although the homework can be done without these definitions. But here's two definitions I want to get up. Definition: the joint PMF of discrete random variables x of 1, x of 2, all the way to x of n. We had talked about the joint PMF when we just had 2 random variables. Well, what is it when we have n random variables? Well, is a function acting on n variables, so it's f of x of 1, x of 2, all the way up to x of n, given by f of x of 1, x of 2, all the way up to x of n equals to the probability that x of 1 is equal to little x of 1, and x of 2 is equal to little x of 2, and so forth, all the way up to big X of n is equal to x of n. Just as we would expect. This is nothing more than an extension of the joint PMF between 2 random variables. Okay, we can do the same thing for jointly continuous random variables where we have n of them. I'll write that over here. We say the random variables x of 1 up to x of n are jointly continuous if there exists a function f of x of 1, x of 2, up to x of n, such that for any subsets, a sub 1, a sub 2, up to a sub n, the subsets of real numbers, the probability that x sub 1 is an element of a sub 1 and x sub 2 is an element of a sub 2 and x sub n is an element of a sub n equals, well, it's equal to this n number of intervals. So here it would be a sub n, we integrate over a sub n minus 1, we keep going all the way up to a sub 1 of f, that's a little f, of x sub 1, x sub 2, all the way up to x sub n. D would be x sub 1, dx sub 2, all the way up to dx sub n. Okay, in this case, f of x of 1 up to x of n is called the joint probability density function of x of 1, x of 2, all the way to x of n. Now, as another definition, we can say that x of 1 up to x of n, a collection of independent random variables, a collection of, I should just say, random variables, is said to be, or are said to be independent if the probability that x sub 1 is element of a sub 1 all the way up to x sub n is element of a sub n is equal to the probability that x sub 1 is element of a sub 1 times the probability that x sub 2 is element of a sub 2 times the probability all the way up to x sub n is element of a sub n. So this is an extension of the definition of math. And this is true for all A1, A2, AN elements of, or subsets of the real numbers. Okay, got a little bit more of a definition, one more definition to give, and an example. And then we'll go through another limit theorem. Well, really our first limit theorem. The Markov inequality, Chebyshev's inequality there. Inequalities, but they don't really have to do with limits of sequences of random variables. The next one will. Next theorem will. So here's a definition. It says random variables x of 1 and x of 2 are said to be identically distributed if their distribution, f sub x of 1 of t, x of 1, is equal to the distribution, if you will, x of 2 of t. Their PMFs are equal, or PDFs are equal, depending on what kind of random variables they are. And as an example, let's let a coin be flipped. And we define x of 1 of heads to be equal to 1, and x of 1 of tails to be equal to 2. Suppose an urn contains a ball is chosen at random from an urn containing 3 red balls and 3 white balls. Then we're going to make a random variable x of 2 define x of 2 of red to be equal to 1 and x of 2 of white equal to 2. Then f of x sub 1 of 1 equals to a half, which also equals to f of x sub 2 of 1, and turns out that f of x sub 1 of 2 also equals to a half, which is what f of x sub 2 is. So they have the same x sub 1 and x sub 2 are identically distributed. They aren't the same random variables. Okay? One of them is a function working on heads or tails. The other one's a function working on the color of the balls chosen. But the chance that of their outcomes being what they are equal to each other. So that's how they're identically distributed. Okay, so here's a fact. It's not something that is mentioned immediately here in our text, but it's called the weak law of large numbers. Okay, and this is a limit law. And it says let x of 1, x of 2, and so forth be a sequence of identically distributed and independent random variables each having finite mean expected value of x sub I. They're all the same. We're going to call them mu. So each one of the each one of the random variable expected value is going to be the same, u, because they're identically distributed. Okay? Okay. And then we'll say, then, I should say, for any epsilon greater than 0, the probability that the absolute value of x of 1 plus x of 2 plus x of n over n minus mu is greater than or equal to epsilon. Okay? This goes to 0 as n goes to infinity. That's what we're going to try to prove. Okay. Now, in terms of the proof, so I'm not going to prove this statement directly. I'm not going to prove this statement. I'm going to add one additional hypothesis. We will prove a variation of the statement as we will assume that the variance of an xi equals to sigma squared, which is finite. Okay, so we'll make that one additional assumption. Okay, so here's what we have. So we let x of 1, x of 2 forever be a sequence of identically distributed and independent random variables. Each having finite mean expected value of xi equal to u and variance. So that's not really in the statement, but we're proving something slightly different than the weak law of large number. We're making this other assumption. Variance of xi equal to, let's say, sigma squared. Okay, then what we're going to do, well, let me back up here for a second and let you look at what we're trying to prove. We're trying to prove that the probability of absolute value of something minus mu is less than or equal to some positive number. Okay? We're trying to say something about that probability. And if we think of this as just one random variable, the sum over n, as one random variable, then this looks a lot like Chebyshev's inequality, or looks like the conclusion, part of the conclusion of Chebyshev's inequality. And that is, in fact, what we're going to use. And so to put ourselves in a position where we can use Chebyshev's inequality, remember, we've got to show that we're going to look at the random variable x of 1 plus x of 2 plus x of n over n. And the first thing we need to do is show that its expected value is what's being subtracted from it inside the absolute value that we're taking the probability of, okay? Being bigger than a positive number. So we want to look at the expected value here. Okay, well, it's kind of involved as a homework problem, but it is a homework problem. This n can be pulled out. Expected value of x of 1 plus x of 2 plus x of n. And as a homework problem, I'm asking you to solve or to show that that's equal to 1 over n, and then this would be the expected value of x of 1 plus the expected value of x of 2 plus the expected value of x of n. Really, I'm expecting you to do this using induction. Okay? However, if you were to try to look at this with the definition, this is the expected value of g, a function acting on x1 through xn, which would either be a summation, depending on these being discrete, or integration of these guys being a continuous, of the x1 plus xn times f of x1 through xn, which would be the joint PMF or PDF, as the case may be. So that's its definition, but I'm not expecting you to go into that in terms of doing the homework, going in that direction in terms of doing the homework problem I've given to you here. But rather, I'd like to just use induction. Okay, so this is what we have. And each one of these guys is mu, so this is equal to 1 over n, and we have n number of mu, so it's n times mu, and that's just equal to mu. That's good. So, as I go to erase the board here, this random variable's expected value is mu. Okay? That's good. And so this fits Chebyshev's inequality, at least the first part of it, perfectly. What we need to do to apply the conclusion of Chebyshev's inequality, we need to see the variance of this random variable right here. So that's what we're going to look at next. So note the variance of x1 plus x2 plus xn over n. Well, by formula, what it's equal to is the expected value of x1 plus x2 plus xn over n. This part to be squared minus the expected value of x1 plus x2 plus xn over n, okay, where all of this is to be squared. Okay. Well, this is equal to, well, this is the expected value of, let me just write this down as is, x1 plus x2 plus xn over n, that got to be squared. And here, this is minus, well, we've already calculated this expected value. It was mu, and we need to square it. That's what we're on. So, and now I'm just going to work with this guy. Note, the expected value of x1 plus x2 plus xn over n to be squared equals, well, it's, here, I'll here. It has the top being squared and the bottom being squared. The bottom's a number, so when it's squared, it's 1 over n squared that can be pulled out front. Expected value of x1 plus x2 plus xn to be squared. So this is equal to 1 over n squared times what will be the expected value of
let's see, it'd be x1 plus x2 plus xn times x1 plus x2 plus xn. Okay. And so that's 1 over n squared times the expected value. If you will, when I'm going to play this out, it's going to be x1 times x1 plus x1 times x2 plus all the way up to x1 times xn. Let me tell you what I just did. What I just did was I took x1 times all of these guys. Now I'm going to take x2 times all of these guys and continue on in this pattern. Sorry. Okay. So plus, now it's x2 times x1, plus all the way up to x2 times xn, plus, we keep going, got a bunch of these guys, and so finally we end up with xn, the last term of the first parenthetical expression, times x1 plus all the way up to xn times xn. So that's what we're taking the expected value of. And the expected value of this sum is going to be the sum of the expected values. So this is going to be 1 over n squared times the expected value of a bunch of these guys. So here I'm going to write down the expected value of x sub I. I'm going to write down this way. It's going to be the sum, as I run from 1 to n, of x sub I squared. The expected value of that. Okay, so what am I doing? I'm going to take the expected value of each part. That's what this is. And that's what I'm going to write here in brackets. The expected value of x sub 1 times x sub 1 is the expected value of x sub 1 squared. I'm going to have later here the expected value of x sub 2 times x sub 2. That's one of these guys when I is equal to 2, and so forth. And the last one's x sub n times x sub n. That's when I is equal to n. But then we've got terms here like x sub 1 times x sub 2, and x sub 2 times x sub 1. So then we've got a bunch of terms here. I'm going to write down some. I don't know how many there are. Of the expected value of x sub I times x sub j, with I being different than j. Okay, they're not the same. And I don't know how many there are. I'm just going to leave it alone for a second. Okay? So this is equal to, here I'm going to say 1 over n squared. I'm going to concentrate on this just for a second. Look, for each I, x sub I squared, they're equal to each other, or the expected value of them are equal to each other. Because they're identically distributed. So this is the same thing as the sum, it's the sum, as I remember, from 1 to n, of just the expected value of x sub 1 squared. They're all the same. These expected values are all the same for square because they're identically distributed. Let's talk about how many of these there are. Well, let's see. These are going to be, well, let's take a look at for each different pairing we have 2 of them. So for each, like 1 and 2 being the index, we're going to have 2 of them involved here. We'd be doing the expected value of 2 of them. Okay. So like if you had x sub 7 and x sub 12, there'd be x sub 7 times x sub 12, and later on there'd be x sub 12 times x sub 7. So there's 2 of them. So I'm going to put down 2. Okay. Now, let's see here. The expected value of x of one of them times x of the other, they're independent. And so that's going to be equal to the expected value of the first guy times the expected value of the second guy. But they're both mu, so it's going to be mu squared here. I got to know how many mu squareds I got. And I got 2 of them for each one of the same numbers involved. But how many different numbers could we have involved? Well, really, if we think back about, we're looking at an x sub 1 plus all the way up to x sub n in one parenthetical expression, and then an x sub 1 all the way through x sub n being added in the second parenthetical expression. And so, really, to get different i's and j's involved, we take the x of 1 through x of n's, and we just want to pick two of them. That's what we're going to have, two different ones here. So how many ways do we pick two different ones? And so here, this is n, there are n of them, and we're going to just pick two. And that's what this ends up being. Okay, so this is 1 over n squared. This will be n times the expected value of x of 1 squared, which I don't know what that is. And then this is plus, this is 2 times n factorial over n minus 2 factorial times 2 factorial, which is just 2, mu squared. Okay. This is going to be equal to 1 over n squared times n. I made a mistake. Let me go back to this. I just made a very simple mistake here. Here, this should be in brackets, and this should be in brackets. So it should have brackets there. Okay. This 1 over n times the expected value of x of 1 squared. And here this is going to be plus. The 2's will cancel out in our fraction, and the n factorial will cancel out with the all of the n minus 2 factorial. Part of the n factorial will cancel out, leaving n times n minus 1 times the expected value of x of 1 squared, which is just mu squared. Okay? That's what we have. Okay, so the variance, that's what we were working on, of x of 1 plus x of 2 plus x of n over n. That's what we were looking at. This guy is going to be equal to 1 over n squared times n times the expected value of x of 1 squared plus n squared times mu minus n mu squared. Oh, this should be squared here. Okay? And remember that's the expected value of the quantity x squared. Minus, it's supposed to be the expected value of x to b squared, but that was just mu squared. Okay, getting the common denominator here, we need this n squared. So I'm going to say this is equal to 1 over n squared. Here I have n times the expected value of x of 1 squared plus here this is going to be n squared mu squared minus n mu squared. And then here, to pull it inside this bracket expression, it's going to be minus n squared mu squared. And then inside this bracket expression, we can cancel some things. We have n times the expected value of x of 1 squared. The n squared mu squared cancels out with this n squared mu squared. And so we're just left with 1 n mu squared, which we can take out. So it's 1 over n squared. Okay. And we can take out an n. And then this is the expected value of x of 1 squared. And I've taken out an n, too, okay, from both of these spots. And so here we have minus mu squared, which is really just the expected value of x of 1 squared. So this guy right here is the variance. So this is 1 over n times the variance of x of 1, which is equal to sigma squared over n. And that's what we got. Okay, that's great. Okay, so the probability that x of 1 plus x of 2 plus x of n over n minus mu is greater than or equal to epsilon, where epsilon is positive, by Chebyshev's inequality. This is going to be equal to the variance. Well, the variance we just found to be sigma squared over n divided by epsilon squared. So this quantity, this probability, is going to be less than or equal to sigma squared over epsilon squared times n. Okay, now let me write something right in front of this. Well, this is a probability, so it's going to be greater than or equal to 0. So let's make that insertion. Okay, well, notice by the squeeze theorem. So since the limit is n goes to infinity of 0 equals to 0, and the limit is n goes to infinity of sigma squared over epsilon squared n, that equals to 0. Then by the squeeze theorem, this probability has to equal to 0. And that's what we're trying to show. So that's the proof of the weak law of large numbers. Okay. Well, this statement that we have for the weak law of large numbers is a type of convergence. And so let me write this down in terms of talking about types of convergence. So, in particular, the weak law of large numbers is an example of a type of convergence for a sequence of functions. Here our functions were random variables. Called convergence and probability. Okay. And so what we're going to do is spend just a few minutes talking about types of convergence for sequences of functions. And we'll just get to the first type today, and that's point-wise convergence. And that's something you saw, I believe, in the analysis class. So here's its definition. It says a sequence of functions f sub n of x, okay, defined on a domain set A, is said to converge on A, provided for each x element of A, the sequence f sub n of x. So this is a fixed x, if you will, for a second. And you think of if f is a function that gives out, let's say, real numbers. You think of these sequence of real numbers of output values, that they converge. And this will allow us to define a function. Okay, so a function, we'll say big F of x, which will be equal to the limit as n goes to infinity of this sequence of functions acting on x. Okay? So for each x this converges, so for each x we define big F to be that number that it converges to. And here I've messed up this definition slightly, and that, well, maybe I'll just add it here. So we say it's said to converge on A, but really I should say to converge pointwise. Excuse me. I forgot this big word, pointwise. In this case, we say f sub n converge pointwise to, I call it big F of x. And we'll just do an example and call it quits with that. So as an example, if you let f sub n of x be defined by x to the n on, so this is my A, from 0 to 1, then it turns out the sequence of f sub n of x converge pointwise to this big F of x, which I'm going to define to be equal to 0 if x is an element of 0 to 1, and 1 if x is equal to 1. And that's what it'll do. Let me just draw some pictures over here. Give an idea. We did this in analysis, but I'll just remind you. So here, I draw the x and y axis. We're looking from 0 to 1. We're looking at, here, let me draw a little bigger. If you look at f sub 1, that's just x to the first. It's y equal to x to the first. F of x equal to x to the first. That's a straight line. X squared looks like this. X cubed is going, this part's going to look like this. And so forth. Okay? If you fix a particular x and look at its output values, their output values are going to get closer and closer to this line, and that's y equals 0. Except when x is equal to 1, because they always, the output values are always 1. That's how we get the result that we do. All right, we'll look at, that's called, well, first of all, that's called pointwise convergence. We'll look at something called almost sure convergence and convergence in probability, which the weak law of large numbers dealt with. We'll do some examples of those, just one or two.
And then we'll talk about something called the strong law of large numbers and the central limit theorem probably next time. Thank you very much.